last time we were basically talking about the variance of a random variable. So if we have a random variable x, we define the first moment, the mean. So this is the first moment or the mean. And this is like the average for the random variable. It is just a single number. If it exists, it tells you something about the random variable. It's just a number, right? It's not a full distribution or anything. And for discrete random variables, this is computed as summation k, and then you take, why I'm saying average, you take the possible values of the random variable and you weight each value by its probability. Okay, so for discrete random variables, this will be the BMF, and this will be the first moment or the mean. Now, the variance of a random variable is a measure of how the values of the random variable basically spread around the mean value. So it tells you by how much, it's like sort of a measure, some measure of how basically the possible values of the random variable spread about the mean value of the random variable. So when we're talking about the variance, we are assuming that basically the random variable has a finite first moment. So we know now the four cases that the first moment may be also plus infinity or minus infinity, or it may not exist. It may not exist as infinity or as a real number. Okay, so here, to make sense of variance, so the assumption is that there is a first moment and it is finite, and we are measuring the spread about the first one. So here's how it's defined. So you take x, the random variable x, and then you subtract the mean. Okay, so it's as if the mean value is like your reference point, and we don't care about whether x is greater than the mean or less than the mean. So one way of doing this is like to square, which means that we care about basically the absolute difference and not about the sign of the difference, and then we compute the expectation of this thing. So this will be the variance, and it is a number from 0 to infinity. And last time we showed that basically the variance of a random variable can also be written as the second moment minus the first moment squared. Okay, and the variance is basically this quantity here is greater than or equal to 0, right? So we are taking this guy here. This is real value. This is real valued and greater than or equal to 0, and so this thing here should be greater than or equal to 0. So we can conclude that the second moment is always greater than or equal to the square of the first moment. So this is a general rule, and it's one of the forms of the Markov inequality that you will encounter later. Okay, so the variance is greater than or equal to 0, and the second moment is greater than or equal to the expected value of x squared. Now, as you have seen in yesterday's tutorial session, that basically the difference between the variance and the second moment is that the variance is the central second moment. So you subtract the mean first before squaring. But then, basically there is this, property that, if the second moment is finite, the variance will be finite and vice versa. Okay, so it cannot be the case like one of the guys is infinite and the other is finite. So they are finite together or infinite together. Now, suppose that you are computing the variance of the random variable ax plus b. So that's a function, a linear function applied to the random variable. You multiply it by a constant a, and then you add b. So what is the first moment first? So the first moment is that you apply the expectation to ax plus b. Now the expectation operator is a linear operator. So basically the expectation of two things that are added together will be basically the sum of the expectations, and b is a constant, so its expectation is itself, and x is multiplied by a constant, and because of the linearity of the expectation operator, you can pull this constant outside, and so this is a expectation x. Okay, so this is the expected value of y which is equal to ax plus b. Now, if you take y and subtract its mean value, so this will be ax plus b minus the expected value of x minus b, and so this constant will cancel out, plus b and minus b, and basically the difference between y and its first moment will be the difference between x and its first moment multiplied by this constant a. Now, to compute the variance is basically this, the expectation of this quantity squared, and so you square, and so you will get a squared, and then you will get this quantity squared. You apply the expectation, again, expectation operator. If there is a constant, you can pull the constant outside, so this will be a squared, and then you are left with this thing, and this thing is just the variance of x. So that here is, a very nice result, that if y is equal to ax plus b, then the variance of y is regardless of b. So the result is independent of b. So b is like, it will always cancel out if you are interested in the variance of y. And then this constant here is squared. So you will get a squared variance of x. Okay, so if y is equal to ax plus b, where a and b are constants, then the variance of y is the variance of x multiplied by the square of this number, which is a. Okay, and from here it's clear that basically when we talk about variances, we don't have like linearity. So linearity, basically that if you have a constant multiplied, by a random variable, if you take the expectation is linear, means that the constant can be pulled outside. Now, if you have a random variable multiplied by a and you compute the variance, now it appears here outside as a squared, right? So variance, generally speaking, is not a linear operator. It's not like expectation. Expectation is a linear operator. Variance is not a linear operator. And if a random variable is scaled by a constant, the variance will basically be the old variance multiplied by this constant squared. And also, if you have now two random variables, and you want to compute the variance of their sum, the expectation of the sum, regardless of what these random variables are, this will be the expectation of x plus the expectation of y. So this is true because expectation is linear. But for variance, this is generally not true. The variance of the sum of two random variables, x and y, is not equal to the variance of x and the variance of y. There will be an extra term that we will talk about later called the covariance. Okay, so basically this is very important to keep in mind, and we will study also the condition that guarantees that the variance of a sum is sum of variances. So under some situation, under some condition, basically you can have equality, but generally speaking, a variance of a sum is not equal to the sum of variances. Let's now try to understand. So the first understanding of the variance is that you basically say, I take x, I subtract the mean. So I am basically trying to investigate the possible values of x relative to the mean. How are the values of x spread about the mean value of x? And so you take x minus expected x, you square, and then you take the expectation. Now let's try to understand the variance, but in another way that will be helpful when we study things like the minimum mean square error estimation and so forth. So suppose that you have a random variable x and you want to guess x, to make a guess about x. Okay. And this guess here will take a very simple form. It is just a constant. Okay, it is just a constant. Okay, like in practice, typically we make guesses about random variables by observing other random variables. Okay, and this will be the topic of minimum mean squared error estimation. But for now, let's assume that we don't have observations, right? We just want to estimate or guess a random variable via a constant. You just want a constant. Now, to make a guess, when you guess something, there is an error, okay? And with an error, you can define this error in a number of ways. Actually, you can define it in an infinity number of ways, okay? So basically here we will define the error in the mean squared error sense, MSE. which is very famous, widely used, and the advantage of using mean squared error in applications is that basically it is much more tractable than any other form of error. So here is the story. So you want to guess random variable x. So you will guess x by a constant now. Again, this may not like be what we do in practice. In practice, we guess using another random variable y. Okay, and so we basically, our estimator will be a function of y, but we don't need to worry about this right now. Now, again, it's a simplified problem in which our guess is just a constant c. Now, x differs from c, so there is a difference between the guys. So you can think of it as the guessing error or the estimation error. Okay, it's the difference between the true thing and your estimate and your guess. Now, how can you sort of like minimize the error? You need like to like write a functional of the error. You need like to express the error in some way that is manageable. And again, the mean square error means that you will square this thing. And when you square the error, it means that you don't care about the sign of the error. So in other words, if c is less than x by something, if it's greater than x by the same thing, those are considered like sort of the same. You don't care about, the guess being greater than or less than. So you square, and then, and then x is a random variable. So you do the expectation. So this is called mean squared error. And the name is like this, error, that's error. X minus c. X is your random variable, c is your guess, so that's an error. Square, so you square the error. Mean, which means that you apply the expectation. So, okay, so now you may say, what if I am not interested in the sign? Can I do something like this? Just take the absolute value without squaring. Yes, you can do. Yes, you can do. You can do many other things. Okay, so this mean squared error thing, again, it's a construct. It's not something that is written to be like the way in which errors are basically measured. It is a choice, and it is a choice for a reason. Again, mean squared error problems are relatively speaking much easier to solve than like solving something with with just the absolute value, not squaring or doing something else. Okay, so so this is like sort of, again, it's a matter, you can think of it as a matter of tractability more than any that it's like the most reasonable thing. It is reasonable, but no one can claim that it's the most reasonable thing. Okay, so we'll take the mean squared error is a way of solving problems like in probability and statistics. And again, generally speaking, it will be that we have a random variable x, and generally later in the course we will assume that we have observations, and we will basically, so y will be a vector of observations. And we want to construct a function of the observations such that the error of your estimation, so the error is the difference between the true thing and your estimator, your guess. And typically we will do the mean squared error thing. Okay, but for now it's as if we don't have observations and we just make our guess based on a constant c. So now what we want to find the minimizer of this guy. So we want to find basically to solve this, what is the minimum value over c of the expectation of x minus c squared, like this. Okay, so how can we solve this minimization problem? So let's start by our objective function. And let's insert the mean value of x. So the assumption, of course, here I am talking about a random variable with a finite second moment. And if the second moment is finite, then we know that the first moment and the absolute first moments will be finite. So this will be guaranteed. And expectation x now is just a finite number. Okay, so take basically this expression here and insert minus the expected value of x plus the expected value of x. You just subtract and add the first moment of x, again under the assumption that x is a random variable with a finite second moment. This expected x will be a finite number. Now, what you do is that you basically expand the square. Now, so you have basically, you can think like we have this term, x minus the expected value of x. This is one term. The other term will be the expected value of x minus c, and then you square. So basically, you get the square of the first term, you get the square of the second term, and then you get double, basically, the product of these two terms together. Okay, so let's study each term. Let's study each term on its own. So basically, the first term here is the variance of x. By definition, this will be the variance of x. Okay. Now, what about the second term? So the second term is the square of this guy. What is expected value of x? It's a number. It's just a number. Minus c. C is another constant. It's this constant that we are hunting for. And so basically, expected x minus c all squared is just a constant, and the expectation of a constant is a constant. It's the exact same constant. So this thing is here. Expected x minus c all squared. Now we have the product of the two terms. We have the product of the two terms multiplied by 2. So let's do this thing. So here is one term, which is x minus expected value of x. And here is the other term, which is expected x minus c. Now this guy is a constant, and expectation is a linear operator. So linear means that if basically your random stuff is multiplied by a constant, you can pull the constant outside. So we can take this guy here, and we can take this guy to the outside with the 2. So we have 2 expected x minus c. And then what are we left with? We have expectation of x minus expected x. This is what we have. So what is this thing? You know, so expectation is linear. Expectation is linear. So what is expectation of this thing? It will be the expectation of the first guy, which is x, minus the expectation of expectation x. This is a constant. And so the expectation of this constant is the constant itself. So it will be expectation x. So expectation x minus expectation x. So this will be a 0. 0 multiplied by basically this thing, which is finite number, will give you a 0. And so you are left with 2 terms. Okay. So what we have proved is that the expectation of x minus c squared, and this thing is equal to the variance of x. Okay, plus basically another term, which is the expected of x minus c all squared. And this term is non-negative term. It is a non-negative term, which means what? Which means that this left-hand side, so the left-hand side, okay, is always greater than or equal to variance of x, right? Because the left-hand side is equal to the variance of x plus something that is non-negative. So this guy here is always greater than or equal to the variance of x. It is equal to the variance of x if and only if basically this extra non-negative term is 0. And this term is 0 if and only if you choose c, you know, this guess to be equal to the expected value of x. So if you choose c to be the expected value of x, this guy will attain its minimum possible value, which is variance x. Again, so we solved this optimization problem by starting with our objective and showing that our objective is equal to the variance of x plus this non-negative quantity. So it means that our objective is always greater than or equal to the variance of x. Is there a possibility of making our objective exactly equal to the variance of x, and this will be like the minimum possible value? Yes, if you can take this non-negative term and make it equal to 0. And can we make it equal to 0? Yes, this term is 0 if and only if small c is equal to the expected value of x. So that's the solution to our optimization problem, which is that basically the minimum of this quantity is the variance. And the minimizer, you know, basically the minimizer, you know, the value of c that is sort of your best guess is the first moment. You would c equal expected value of x, and the minimum of this quantity will be the variance of x. So here, sort of an understanding of the mean of the random variable, the first moment, and the variance. So now we can say that what is the first moment? it is, the first moment of a random variable, and we are talking about a random variable with a finite first moment. It is basically your best guess. It is your best guess. It is your optimal guess about the random variable. Okay, about the random variable. You cannot just say best or optimal, right? Again, because it is you who define the sense of optimality. So this is the first moment is the best guess in a mean squared error sense. So if you measure the error using mean square, MSE, mean squared error idea, then in that case, your best constant guess for a random variable is basically its first moment. Okay, and so basically, if I tell you that, I am going to generate a random variable, what is your best guess? And you tell me no other information, just to make a guess. Well, according to this formulation that we have right now, your best guess will be the first moment. If you change mean squared error and use some other criterion, this result will differ. So it is optimal in the mean square error sense. So this is like sort of, again, a good interpretation of the first moment and the variance, which will help us in the more complicated problem of minimum mean squared error estimation when we use some random variables to estimate other random variables. Here we are basically solving the dull problem of just making a guess about a random variable using just a constant. You have to say a number, just a number, okay? You are not making use of observations or anything else, okay? So the minimizer is the first moment, and the minimum value of your mean squared error, so MSE min, the minimum mean squared error, is the variance of X. Okay, so this is another way of understanding the variance. Again, will be useful. It's actually useful in solving some inequality problems, and it will help us in MMSE estimation. Okay, now let's start talking about inequalities. Probability is full of inequalities. We have tens or hundreds of inequalities. Some of them are very sophisticated. So we'll start to build our database of probability inequalities, starting from the most straightforward one, and actually one of the most important inequalities, which is the Markov inequality, because the Markov inequality itself can be used to construct further inequalities and powerful things like the Chernow bound and so on that we will talk about later in this course. So the Markov inequality is something that you apply when you have a non-negative random variable. So Markov non-negative random variable. So it's not something that you apply to a general random variable, non-negative. Okay, so this is our first business. It must be a non-negative random variable. For a non-negative random variable, we are sure that the first moment exists either as a finite real number or basically as plus infinity. Let's suppose that we have a parameter A that is positive. The Markov inequality is basically it is an upper bound. So it is an upper bound on the tail probability, which is what is the probability that this random variable X will go above A? What is the probability that X is greater than or equal to A? Okay, so this inequality again, we have this thing, it's called the tail probability in the sense that you ask yourself, what is the probability that random variable X will be greater than or equal to some given threshold value, which is A? And you will not compute this upper bound exactly. You can compute it exactly if you have like the distribution of X. But let's suppose that you have, you don't know except the mean of X. Can we know the mean of X not to obtain the probability exactly, but to have an upper bound? Okay, so we want this probability to be less than or equal to something. So, and we are hunting for an upper bound. We are hunting for an inequality. Okay, and sometimes this is the best you can do. It's the best, like to do in practice. You can just have an inequality rather than an equality, and sometimes these inequalities are very useful in theoretical derivations. Okay, so here is the way to go. First order of business is a trick that you have seen in the previous lecture, maybe you have seen in yesterday's tutorial session. It's very important, right? So you start with the expected value of x, and what you do is that you insert these two indicators, basically partitioning the possible values of x. The possible values of x are either that x is less than a, strictly less than a, or that x is greater than or equal to a. Okay, so this is the first order of business. You take x, you imagine that x is multiplied by, it is multiplied by 1, and then you write this 1 as the sum of two indicators, and these two indicators, one of them is 1 and the other is equal to 0. And so one indicator will be indicator x greater than or equal to a, the other will be indicator x less than a. And then by the linearity of expectation, you can basically split this expectation into two terms. So the first term will be the expected value of x multiplied by indicator x greater than or equal to a. The second will be expected x indicator x less than a. Okay, so let's try to think about basically those terms. So let's think about this guy here. Okay. So claim that x indicator x greater than or equal to a is in fact greater than or equal to a indicator x greater than or equal to a. Okay, and this statement is like sort of deterministic. So like if you fix a value of x, then this is true. And again, the best way like to verify this thing is like to basically investigate the possible values of the indicator function. There are just two possible values. So there are two cases. The first case is that x is less than a. If x is less than a, both indicators are equal to 0, and we have 0 greater than or equal to 0, which is a valid mathematical statement. Now, if x is greater than or equal to a, then the indicator is 1, and basically we have from here that x is greater than to a. And if x is greater than or equal to a, then x is greater than or equal to a. Again, it's a perfectly valid logical statement or mathematical statement. So this basically inequality is true. It's true for like any real number x. Okay, so basically you can say this is always true, and now you know that x is a random variable, so remember that we have this rule that if you have two random variables y and z, and y is greater than or equal to z almost surely, then you can take the expectation of both sides. Then expectation y is greater than or equal to expectation z. Okay, so this is what we'll do here. So this is true. If this is always true, or like professionally speaking, you will say that it is true almost surely, or with probability 1, then you can take the expectation of both sides. So you can take the expectation of basically of this side and of that side. Okay, so now what is now our conclusion? So expected x, again, by using the trick of the two indicators, it is split into two guys like this. Now, what is this second guy? The second guy is non-negative, right? Because x is a non-negative random variable. So the expectation of a non-negative random variable is a non-negative quantity. So this guy is greater than or equal to 0 because it is non-negative. The indicator function is 0 or 1, and x, we start with a non-negative random variable. So expected x is equal to this first expectation plus a non-negative quantity. So we know that expected x is greater than or equal to the expectation of x indicator x greater than or equal to a. So we are sure about this. And then using basically our inequality from here, then this is greater than or equal to expectation of a indicator x greater than or equal to a. Now, a is a constant, so we can pull it outside. So this is equal to a expectation of the indicator x greater than or equal to a. And in the previous lecture, we talked about the expectation of a Bernoulli random variable, or a random variable that is 0 or 1, right? So what is the expectation of an indicator? So basically, it is 0 times the probability that the indicator is 0. Well, that's 0. Plus 1 multiplied by the probability that the indicator is 1. And so we always say that basically expectation of an indicator, it will give you the probability of this event here, which is a probability that x is greater than or equal to a. Now, so this is basically what we have right now, that the expected value of of the non-negative random variable x is greater than or equal to a, multiplied by the probability that x is greater than or equal to a, divide both sides by a, which is a positive constant. So the probability that x is greater than or equal to a is upper bounded by expected value of x divided by a. And again, so this is the Markov inequality. X is a non-negative random variable. It's a non-negative random variable, and a is a strictly positive constant. Okay, and so this is basically what we have, and is called the Markov inequality. Again. Is it it's used a lot. I cannot claim that it's the solution to every problem under the sun, but it is used a lot. Like, so for example, you can basically I have seen so many problems in which you use this. So the idea now is, I mean, it's if you want to learn, basically that you should try to generate things like the proof of the Markov inequality and the problems that you have seen in yesterday's tutorial session by yourself. Okay, so don't just follow and that's it. Try from mind, just without seeing any, try to do these derivations. Okay, these tricks, again, it depends on who you are. So, it may be the first time in life to see these things done, and they will appear hard, and so you need that you train yourself. Or maybe you have taken like a previous course on real analysis, and everything here will seem like super trivial. So it depends. I mean, I cannot like say a statement that is, that fits all of you. But especially if you are basically doing these tricks for the first time, it's not just that you look at them. No, you must be able to, to basically go away, grab a white sheet of paper and a pen or a pencil, and then write this derivation from mind. It's not that you are memorizing. It's not memorization. It's logical flow, right? It's as if you are sliding. If you think about it, it's like you start at some step and you go down by step. It's as if by the law of gravity, right? It's like sort of, there is like a logical structure that will lead you from one step to the next. So make sure that you basically redo all your derivation again in the correct way. If you just have a look, and then in the exam, I don't think you will be able like to reuse those guys whenever needed. Okay, what is the question?
Professor, can you repeat very quick what you did after the step of linearity of expectation? I'm kind of confused of what your argument was.
Okay, no problem. So basically we started by this. Okay, here it is. Okay, x. And then you say, okay, I will basically partition this, exploiting linearity of expectation. I have two possibilities, that x is greater than or equal to a, or I have that x is less than a. Okay, so this is the first step. Okay, you can do it like in slow motion. So in slow motion, you will take a one here, the one here, okay, and split it into, write it as the sum of two indicators, and then you do the summation. Okay, so you can do it in slow motion. After a while, you will get used to these things and do them quickly. Now, we are talking about a non-negative random variable. So this thing here is greater than or equal to 0. And if it's greater than or equal to 0, then this whole thing here is greater than or equal to 0. Now, you have a something which is expected x is equal to this thing plus a non-negative quantity. So to get this thing, you need to add this thing to something non-negative to get the expected value of x. So from the beginning, we know that expected x is greater than or equal to the expectation of x indicator x greater than or equal to a, right? So in other words, expected x is just greater, because both terms are actually non-negative. It must be the case that expected x is greater than or equal to just one of these two non-negative terms, which here our focus will be the first term. Then the claim is that, okay, so this is something that basically, so this was like sort of a side step that you do, is you say that this x here, indicator x greater than or equal to a, is greater than or equal to a indicator x greater than or equal to a. Okay. And it is inspired actually by the indicator that x is greater than or equal. So basically you replace the x by a, okay? Again, motivated by the fact that the indicator is x is greater than or equal to a, which means that it may be the case that x is less than a, and if x is less than a, then both indicators are basically, so this is case one, that x is less than a, and both indicators will be 0, and you have 0 greater than or equal to 0, which is correct. Then case two, x is greater than or equal to a, that's when our indicator is equal to 1, then basically you have x greater than or equal to a. So if x is greater than or equal to a, then x is greater than or equal to a. That's, you know, that's a correct logical statement. So basically this is true, and it's true, you know, here I did not even consider x to be a random variable. This is true for any like real number x, okay? So we have a property that if you have a statement that is true deterministically, okay, or true with probability 1 or true almost surely, then actually you can take the expectation of both sides. So basically from here you can say that expectation of x indicator x greater than or equal to a is greater than or equal to expectation the other guy, which is a indicator x greater than or equal to a. Okay, so this is what I will copy here. So here we will say that this thing is greater than or equal to expectation a indicator x greater than or equal to a.
This statement didn't come follows like from the proof, like this is like a side and then you use it in the proof, right?
Yes, yeah.
Okay.
Yeah.
Yeah.
So it's basically a lower bound. It's a lower bound on this term here. Okay, it's a lower bound on this term here. Okay, and then we put it here. Okay, and then we are done. You know, we just have two steps. I mean, basically use the properties of expectation. So the first thing is that this is a constant, so you pull it outside, and then you have the expectation of an indicator, or you know. And so what is expectation? So it's the possible value multiplied by its probability. So the indicator is 0 or 1. So basically the expectation of any indicator will be 0 times the probability that the indicator is 0. Well, that's 0 because you are multiplying by 0, plus 1 multiplied by the probability that the indicator is 1. So basically, I said it in the previous lecture that the expectation of an indicator is the probability of this event that you have inside the indicator. So it is the probability that x is greater than or equal to a. And that's it. This will be basically Markov inequality, but typically it is written as, you know, not as a lower bound on the first moment, the way we typically write as the Markov inequality as an upper bound on the tail probability. What is the probability that x is greater than or equal to a? So this probability, you know, you can make a guess regarding this probability if you know just the first moment of x. So suppose that you don't have you don't know the distribution of x, you only know one number about x, that it is, you know, you know that it is a non-negative random variable with this particular first moment, then you can upper bound this tail probability by the expected value of x divided by a. Okay, so this is the Markov inequality. So let's basically try to apply it. If x is an exponential random variable, exponential random variables are non-negative, and generally speaking, exponential lambda is a random variable whose PDF is lambda x e to the minus lambda x indicator x greater than or equal to 0. So that's the PDF. Okay, and the first moment of the random variable is 1 over lambda. Okay, so here we take exponential 1, and for exponential 1, it means that the mean is equal to 1. Okay, so what will be Markov inequality? So for this guy here, what is the Markov inequality? Probability that x greater than or equal to a is less than or equal to the first moment, and it's 1, okay, divided by a. So this is the upper bound. The upper bound, you know, from Markov inequality will be 1 over a. Now, of course, in this case, we know we can compute this probability exactly because, you know, we assume that we know the random variable. So this probability exactly equal to, so this is not a bound or anything, it is the integral right? If we have a continuous random variable and we want to know, what is the probability that the random variable is greater than or equal to a, we simply take the PDF of the random variable. In our case here, it will be e to the minus x, and we integrate over basically, this range. So x is greater than or equal to a, so a to infinity dx. Okay, and so you can actually compute this probability exactly, and it will give you e to the minus a. So in fact, we know the actual probability, and this is the upper bound. This is the upper bound on the probability. Okay, and so let's basically see the relief. So this is the probability x greater than or equal to a, and this is the parameter a, which is some positive parameter. So the true probability, the exact probability, is this black curve here. Okay, and it decays exponentially. It is e to the minus a. The Markov upper bound, and Markov upper bound is basically the expected value of x divided by a as we derived it. In our case here, because our random variable is exponential 1, it will be 1 over a, and so it is this red line. And as you can see that there is a difference, it's a big difference, okay? And here is a redrawing, and this is like a logarithmic scale right here. So here it's a logarithmic. And you can see that basically this upper bound is lousy. So the actual probability is decaying very fast. It's decaying exponentially, but the Markov upper bound is decaying as 1 over a. And as you can see that the relative difference is basically increasing significantly. Okay. However, it is still an upper bound. Okay. And again, to compute the exact thing, you are assuming that you know the distribution. Okay, you know the distribution. So in practice, sometimes we don't know the distribution, and we can just estimate the first moment. So the Markov upper bound is generally not a tight upper bound. So a tight upper bound is an upper bound on something that is close, close to the true or the exact value, right? But it is not. It is not a basically tight upper bound. Not only this, basically the upper bound can exceed 1. See here in this curve. So basically this is the Markov upper bound, and if a is small, so if a is less than 1, basically the upper bound is greater than 1. And it's sort of useless, right? So basically if I tell you, oh, I have an upper bound on the probability, it is less than or equal to 1.4. Well, it's useless statement because we know that probabilities are less than or equal to 1, right? So the Markov upper bound, yes, it can exceed 1. It will be a mathematically correct statement, no doubt, but it's useless, right? So it is sort of a useful bound if it is less than 1, because in any case we can upper bound any probability by saying that it is less than or equal to 1. Okay, so again, from this just simple illustration, comparing the Markov upper bound and the true probability, we can see that the Markov upper bound is not tight. Okay, sometimes it's far from the actual probability, and sometimes it exceeds 1, rendering it sort of useless. But it is, again, it's good, and we can use it likely to do better things, as we will do right now. So here's a trick, like sort of, can we obtain a better upper bound, assuming that, for example, we know a higher moment of the random variable x. Okay, so here is the trick. X is a non-negative random variable as before. A is a positive parameter, and also we are interested in the probability of this event that x is greater than or equal to a. Now, if x is non-negative and a is positive, then actually if x is greater than or equal to a, this is true if and only if x to the power r is greater than or equal to a to the power r, right? So you don't have just to work with x greater than or equal to a, you can just raise this to some power. R maybe 2, maybe 3, maybe 4, and so on. Right, so you have an inequality, and both sides of the inequality are non-negative. That's great, because raising it to some power will not change the sign or do something that may confuse us. So you can just basically raise to the power r, and then you can take the rth root of both sides here to get this one. So these two guys are the same. So the trick is to say that this event here, For non-negative random variables x and for a positive a, this event is equivalent to x to the r greater than or equal to a to the r, so they have the same probability, right? Because if x is greater than or equal to a, then x to the r is greater than or equal to a to the r, and vice versa. If x to the power r is greater than or equal to a to the power r, then x is greater than or equal to a. Just take the rth root of both sides. Again, this is true because, because of this non-negative thing. So what you can do is that you can apply Markov inequality. You can apply it to x to the power r, right? So now you can think you have probability x greater than or equal to a is equal to probability that x to the power r is greater than or equal to a to the power r. Okay. Now you can think of this random, x to the power r as a new random variable. It's a new non-negative random variable. Let's call it y. Okay, so it's a new non-negative random variable. So apply Markov inequality. So what is Markov inequality? It tells you that you can have a tail probability like this. You can upper bound by the following. You can upper bound by a fraction. Then numerator is what? Then numerator is the first moment of this non-negative random variable. So it will be the expected value of y, which is the expected value of x to the power r. Okay, and then in the denominator you have this thing here, which will be a to the r. Okay, so this is basically what we have. So again, this derivation, it relies on Markov inequality. Again, it's just one line derivation. Let's do it again. That basically the probability that x is greater than or equal to a, I can now, before doing the Markov step, I can raise both sides to the power r, and I have an equality here because basically x and a are non-negative quantities, so raising them to the power r or raising them to the power 1 over r, I mean, basically these two guys are the same. If this is true, this is true. If this is true, this is true. The events are equivalent, and so they have the same probability. Now apply Markov inequality to this thing. So this is less than or equal to. Markov inequality is this. You have a non-negative random variable. So in the numerator, you put the expectation of this non-negative random variable. And then you divide by this guy here, which is a to the power r. Okay, so we can basically get ourselves 1 degree of freedom, a parameter to play with, which is this r. So you can see that the Markov inequality itself may not be like, that useful. It's useful actually in some derivations. So even if it's like not used in practice, but it is in computing things, but it is useful in derivations. But also it can be modified so that it becomes more and more useful by playing with this parameter r, right? So I did the same thing to the previous example. So this is the exact probability. Okay, so this is this. No. Now I have the Markov upper bound with r equals 1. This is the conventional Markov bound that we did. It is the red line, and you can see that the red line, it's so the distance between the red line and the true probability gets, this guy decays slowly, and this guy decays like this. So the distance is increasing. But if you use r equals 2, okay, if you use r equals 2 here. Okay, then you get a bound that, you get this green one. If you use r equals 5, then you get this one here, and so on. Okay, so you can get like sort of a better. Of course, there is a cost, or there is like, if it's more assumption. The assumption is that actually those moments, okay, so expected x to the r is some good finite number, right? Because like you may have a non-negative random variable with a finite first moment, but starting from the second moment and higher, basically the moments are infinity. And if they are infinity, then you are saying that the probability is less than or equal to infinity, which is again a useless statement, right? So I mean, it's like, those guys will work and will give you better upper bounds on the tail probability, assuming that, those moments are finite, they are finite. And you can start getting like better upper bounds, in some situations. In some other situations, this may not work. Later in the course, we will study the Chernoff bound, and the Chernoff bound is a trick that is like this, but rather than raising both sides to the power r, what we will do is that we will exponentiate. So we'll basically take e to the power both sides. We'll see this trick later and talk about it in details. It's a very powerful trick that is widely used in probability and statistics. Okay. Another manipulation for the Markov inequality will give us the Chebyshev inequality. So suppose that we have again a finite first moment, and so now our random variable does not have to be non-negative. Okay, and then it has a finite first moment. Here it is, which is some finite real number, and x again here, it does not have to be non-negative. Then you subtract, okay, no problem. Then you take the absolute value, okay. So this thing here will be non-negative. It's a non-negative random. It is a non-negative random variable that we have here, okay. And so we ask ourselves, what is the probability that absolute x minus expected x is greater than or equal to a? Okay, so here we are basically trying to investigate the probability that x deviates from its first moment. Okay, what is the probability that the quote-unquote the distance between x and its first moment exceeds a threshold value that is a? So how can we upper bound this probability? Again, our friend here is Markov. But before doing the Markov inequality, what we will do is, as I did on the previous slide, we will square first. So you will raise both sides to the power 2, something again that is valid, and it is not problematic because our stuff on both sides of the inequality is non-negative. So we will square first, okay, and then we apply Markov inequality to this probability. So what is Markov inequality? It tells you this probability is less than or equal to then something over something. The thing that you have in the numerator is the first moment of whatever you have, the expectation of whatever you have here. It must be a non-negative random variable, which is what we have here, and so we take the expectation of this thing, which is x minus expected x all squared. And then you divide by basically this thing. Okay, so it's this over that, and what we see here is simply the variance of x. So this is our inequality. It's called the Chebyshev inequality. As you can see, it's just one line that is derived from the Markov inequality. So it is like a daughter of the Markov inequality, okay? But you can call it Markov also. You can call it Chebyshev inequality, and it is another bound on probability that you can use. So the probability that the absolute of x minus expected x greater than or equal to a is upper bounded by the variance of x over a squared. Now, if the variance of x is infinity, okay, so well, this will be a correct statement. It's useless but correct, right? Because every probability is less than or equal to infinity. In fact, again, if the upper bound is greater than 1, then well, it's useless, right? So you find these things more useful if basically the upper bound is less than 1. Okay. Now let's basically prove two very important statements regarding random variables and their moments. So if a random variable x is non-negative, and someone told you that basically the first moment of x, the expected value of x is 0, it is exactly equal to 0, then it must be the case that x is 0 almost surely. X is equal to the constant 0 with probability 1. Okay, so basically this is the statement, and let's prove it. So the idea of proving it, so x is non-negative, right? So if x is non-negative, what is this probability? Probability that x is greater than or equal to 0. What is this probability? One, exactly, it is 1, right? Because x is non-negative, so it is guaranteed to be greater than or equal to 0, exactly. Okay, so here is the trick. Now, suppose that x, so what is this probability? It is the probability that x is exactly equal to 0 plus the probability that x is strictly greater than 0. Okay, so this is equal to 1. Okay, so this is true for any non-negative random value. So to show that x is equal to 0 almost surely, or with probability 1, we basically, our goal here, so our goal is to show that probability that x is strictly greater than 0 is equal to 0 when expected x is 0. Okay, so this is how we will prove this statement. So we want to show that if a random variable x is non-negative and its first moment is equal to 0, then x is equal to 0 almost surely. So, well, x is non-negative, so it is greater than or equal to 0 with probability 1, so it may be 0 or strictly positive. So to say that it is equal to 0 with probability 1, it means that the probability that x is strictly positive is 0. So we need now to show that the probability that x is greater than 0, that this probability is equal to 0 when, basically the first moment is equal to 0. So how can we show this? The problem with, if you work with the probability x equals 0, how can you employ the Markov inequality, right? So I mean, to show you that, probability, so Markov inequality tells you something like this, that this is less than or equal to, and then you divide by a, right? So if you have 0, right? If you have 0, and so if you divide by 0, you get infinity, and the upper bound is useless, right? So this is sort of the trick here. The trick is that we want to investigate the probability that x is strictly positive, and so we want the probability that x is greater than 0. So Markov is not ready for this, right? Because for Markov, and note that the statement is independent of the distribution, right? So so here we are not making, we just know that x is some non-negative random variable. So so we have to use Markov, but again Markov is not ready because you will have basically the threshold is 0, and a threshold of 0 in Markov inequality, it will make the upper bound infinity. So here is the trick, and again, it's one of those tricks that are used a lot, is that the event that x is equal to 0, the event that x is greater than 0, the event that x is greater than 0 is equivalent to the union of events that x is greater than or equal to 1 over n for every natural number n. Okay, so basically this will be the trick. So why is this true? Now suppose that, I mean, you can show, you need to show that these two guys are the same. So if there exists m that is a natural number and x is greater than or equal to 1 over m, right? If there is a natural number, let's say a trillion, and x is greater than or equal to 1 over trillion, then x indeed is greater than 0. Okay, so if you can find a natural number such that x is greater than or equal to the reciprocal of this natural number, then no doubt that x is a positive, it is a positive number. Now the other way, now if x is greater than 0, then there exists some natural number v such that x is greater than or equal to 1 over v. And actually we can find a formula for this v, right? What is the formula for the v? Well, take the reciprocal of both sides of the inequality, so 1 over x is less than or equal to v. So you just need to choose v greater than or equal to 1 over x. So if you know that x is positive, you can always find some natural number. Basically, the natural number will be greater than or equal to 1 over x, and in that case, it will be, that x is greater than or equal to 1 over v. So basically, these two are equivalent to one another. So to say that x is strictly positive is to say that there exists a natural number such that x is greater than or equal to 1 over n. Okay, so this will be our trick to basically make the Markov inequality valid in our case. Okay, so so here is again, you take x greater than or equal to 0. A direct application of Markov is useless because you will, like, if you stretch things and assume that your parameter a is allowed to be 0, you will divide by 0 and the upper bound will be infinity. So no, you take that this event is equal to the event that there exists some natural number that x is greater than or equal to 1 over n. Now you apply the continuity of probability. So let's see why it's valid in this case. So those are the events that x, so if n is 1, we are talking about x greater than or equal to 1, right? X greater than or equal to 1. If n is 2, we are talking about x greater than or equal to 1/2, right? And if n is 3, then we are talking about x being greater than or equal to 1/3, and so on, right? So, basically we have here events n, a, n, and what do these events look like? They are nested, right? A1 is contained in A2, is contained in A3, and so forth, right? Because, the first one is basically the interval from 1 to infinity, second one from half to infinity, third one is from 1/3 to infinity, and so forth. So we have the continuity of probability in its, the nested version, which tells you that the probability of this thing is just the limit of n goes to infinity, the probability of x greater than or equal to 1 over n. So here a friend helping us again, it helped us in proving the Borel-Cantel lemma, and here it is striking back, and very useful. It's very useful. Now what you need to show is that, that basically this probability that x is greater than 0, you can find the probability that x is greater than or equal to 1 over n, which is a positive number, and then take the limit. Because this guy now is a positive number, we can apply the Markov inequality. Okay, so what is, so what by Markov, what is this thing? The probability that a non-negative random variable is greater than or equal to something, then if this is less than or equal to the expectation, the first moment of the random variable, and then you divide by basically this thing, which is 1 over n. Okay, so this will give you basically that the probability that x is greater than 0 is less than or equal to the limit as n goes to infinity of n, the expected value of x. Now we have a given. The given is that expected value of x is equal to 0. So this guy is 0. I mean, this is from the problem statement. So our sequence is the all 0 sequence, right? So regardless of n will always be multiplied by this 0 because we are investigating a non-negative random variable whose first moment is exactly equal to 0. So we have the all 0 sequence, and the all 0 sequence converges to 0. Okay, so this probability is 0. Now, so what we proved is that the probability that x is greater than 0 is less than or equal to 0, but we know that probabilities are always greater than or equal to 0, so the probability that x is greater than 0 is 0. But we know that x is greater than or equal to 0, so it must be the case that the probability that x is exactly equal to 0 is 1. And this is what we say, this is what we mean when we say that x is equal to 0 almost surely. We mean that the probability that x is equal to 0 is equal to 1. Again, so the trick was to show that the probability that x is strictly greater than 0, basically that this probability is 0, and we showed it using Markov, but after doing this, using this idea here, because Markov will fail for a direct application, so the trick was basically to replace this event by this union, and then to use the continuity of probability. And then to apply Markov to this guy here. Now 1 over n is a positive number. Now a similar result is, what if you have a random variable and the variance of this random variable is exactly equal to 0? So if you have a random variable and this random variable, its variance is 0, then it must be the case that x is equal to a constant almost surely, and this constant is nothing but the first moment of x. So if you have a random variable, and if the variance of the random variable is equal to 0, it must be the case that x is equal to the expected value of x almost surely with probability 1. Now, basically, our proof here is like sort of a copy and paste. It's just we modify things to involve the variance. So let's see. So you start with this probability, the probability that absolute x minus the expected value of x is strictly greater than 0. So we start with this point. What is the probability that, you know, the distance between x and its first moment is strictly positive? So you apply the previous trick. You say, okay, the being positive means that there exists a natural number such that this absolute value is greater than or equal to 1 over n. Then you apply continuity of probability. So basically this probability of a union, you can find this probability and then take the limit as n goes to infinity. And so we have this probability here. Now to this probability, we can apply the Chebyshev inequality. So by the Chebyshev inequality, what is this probability? The probability that the absolute value of a random variable minus its first moment is greater than or equal to a positive number is upper bounded by, in the numerator we put the variance of the random variable, which is variance x, and in the denominator we put basically this guy here, which is 1 over n. So variance x over 1 over n, and so this will give you 1 over n squared. Sorry, so it is like here in the Chebyshev inequality. So if we have a, then we have here a squared. So here, if we have 1 over n, it will be 1 over n squared. So we get n squared variance x. But it's given that the variance of x is exactly equal to 0. So n is for every natural number n. For every natural number n squared times variance of x is 0, because it's given that the variance is 0. So we have the all 0 sequence, so its limit is 0. So the probability that absolute x minus the first moment strictly greater than 0 is 0. And if it's 0, then it must be the case that the probability that this absolute value equals 0 is 1. Okay, so basically the absolute value of x minus expected x equals 0. This happens with probability 1. It happens almost surely. And we know that the absolute value of something is 0 if and only if this thing is equal to 0. So it must be that x minus expected value of x is 0. So it must be that x is equal to expected x almost surely. So here we mean that x is a constant random variable, or sometimes we say it is a degenerate random variable with probability 1 or almost surely. Specifically, x is equal to its first moment. Okay, so this is, I think, like someone in the previous lecture asked about the situation of a variance equals 0. This is its meaning. If the variance of the random variable is 0, then the random variable is a constant almost surely. In fact, the random variable is equal to its first moment. Okay. Now, in applications, we are typically interested not in just one random variable, but in a bunch of random variables, multiple random variables, or let's call them random vectors. Okay, so in practice, we typically deal with random vectors. In fact, we can deal with, like, in some applications, thousands, millions, billions of those, of those guys. So a random vector. Okay, so a random vector is a vector whose components or whose elements are random variables. And formally speaking, basically the random vector x is a function, is an f measurable function that you define from the sample space to the n-dimensional real space. Okay, so like if you have just a two-dimensional random vector with two components, then basically what you do is that you take each element in big omega and map it to a point in the plane. Generally, you will map it to a point in the n-dimensional Euclidean space. Now, any mapping is a function, okay, but to be a random variable, you need this thing, you need that basically every Borel set in the n-dimensional Euclidean space its pre-image should be F measurable. Okay, so this story is still there, and sometimes it's needed, like when you study things like almost sure convergence of random vectors and so on. But now let's just focus on the random variable, and forget sort of about how it's related to some sample space, and this thing of regarding being a measurable function. And so let's be like a bit more practical. But of course, the measure theoretic story is still there, and not any function you define from big omega to the n-dimensional Euclidean space will be a valid random variable, and so forth. Okay, so to be like more practical, again, in practice, what we do is that we care about typically not just one numerical outcome of an experiment. Typically, we care about a collection of numerical outcomes. So here the example in the notes, that if you like throw a dice 10 times, so what do you get? So you get basically 10 results. Okay, so you get 10 results, and each result will be what? Will be a number from 1, 2, 3, 4, 5, 6, right? So first throw, you will get like 1, then 2, then 1 again, then 3, then 6, and so on. So basically your sample space is, big omega will be basically its elements. The elementary outcomes will be basically sequences composed of 10 numbers. Each sequence is composed of 10 numbers, and each number will be a number between 1 and 6. So how many elements do we have in the sample space? It will be 6 times 6 times 6, 10 times, so it will be 6 to the power 10. Okay, so those sequences are basically our sample space. Now, how do we map them to real numbers? It depends on what we are doing in life. So you may be interested in a number, basically some basically numerical results, like the number of rows in which 2 is obtained, right? So this may be one of the resulting sequences, and maybe your interest for some reason is that you need to take this sequence and assign to it a number that is basically the count of the number 2. So how many times number 2 appear in the sequence? So here 2, it's 1, 2, 3, 4. Why are you obsessed with the number 2? Why do you count it? Again, I mean, maybe this is what you are doing in some experiment. But you may be, basically obsessed with something else. You may be obsessed by the sum of those 10 numbers, or basically by how many distinct numbers that you get. Right, so here, if this is the resulting sequence when you roll the dice 10 times, you may be interested in, what numbers appeal to you. So here, you never get a 1, you never get a 2, but you get 3, you get 4, you get 5, you get 6. Okay, so maybe you are interested in the number of distinct numbers that appear. So in this case, it will be 4. For random vectors, again, sometimes you are interested in all these at the same time. So that's the reason you are basically not interested in just one numerical result related to the outcomes. You are interested in a bunch of them at the same time. Okay, so what you do is that you imagine, you can imagine that you have not just one random variable, but several random variables, and you can think of those as components in a vector, and this vector will be called a random vector. Okay, so this is very important. Again, like in practice, it's rare that like you have one application, you just have a single random variable. Typically, we have, again, many of these. So now the question is, how do we characterize random vectors? Do they have like sort of a CDF? What are the properties of this CDF? And so on and so forth. Okay, so let's start by the CDF. Like for a single random variable, the CDF is defined for all types of random vectors. Okay, and a CDF now is a function, okay, that is basically defined as such a probability. So for one random variable, single random variable, x, The CDF is basically the probability that the random variable is less than or equal to small x. Now, if you have a random vector, and so you have a bunch of random variables, let's say big N of them, then now you have something called the joint CDF, and it is the probability that big X1 is less than or equal to small x1, and big X2 is less than or equal to small x2, and big X3 is less than or equal to small x3, and so forth. Okay, so this is basically the joint CDF. And sometimes it's written as this, so you have as your superscript your random variables, and here you have x1, x2 up to xn, and so you say that what is the probability that this guy is less than x1, this guy is less than x2, and so forth. Or you can write things in the compact way, but it is understood. Intersection, yes, it's and. Yes, it is intersection, and. So here this comma is intersection, or and. Okay, very important. It's the probability that x1 is less than or equal to small x1 and x2 is less than or equal to small x2, and so forth. Okay. Now, what are the properties of a joint CDF? Those properties, like for the single case, they can be made like continuity of probability, but we will like try to understand and use them directly. So, here's the first property. So, the CDF is this probability. Xn. Now, what if you take the limit as one of those guys goes to infinity? Is it for us that one of those guys, its value, x big, x k less than equal to minus infinity, that it has the probability of 0, right? Because of you find them mean values. Okay, so they are in number. So this is okay. So if you take any one of those guys and take the limit as one of so if any one of those guys, any one of those guys. So this is true for every k. So for every k is 1, 2. So can you now the joint CDF, and we are asking ourselves what basically one of the guys is less than or equal to minus infinity, and it can be anyone. So what is the probability that a random variable is less than or equal to minus infinity? That's a 0. Okay, so this will be a true statement that if you take the joint CDF and take the limit as xk goes to minus infinity, then for every k this guy will be 0. Now, suppose that you change your story and now you take the limit. You take the limit as every small x going to plus infinity. Okay, so x1 going to plus infinity, x2 plus infinity, till xn going to plus infinity. So you're asking what is the probability that x1 is less than or equal to plus infinity, x2 is less than or equal to plus infinity, xn is less than or equal to plus infinity. Well, I mean, those are random variables. They are basically maps from the sample space to real numbers, and so everyone is less than or equal to plus infinity. So this limit here will be equal to 1. Note the difference that in the first case you take the limit with respect to any one of them. So if you ask, what is the probability that x3 is less than or equal to minus infinity, this should give you 0, and the same should apply if you ask about any other random variable, any other component of the random vector. But in this case, if all of them, if you ask what is the probability that x1 is less than or equal to plus infinity, x2 less than or equal to plus infinity, and so forth, then this probability is 1. In each of the variables, the function also will be right continuous. So basically this property is satisfied. And then we have, rather than the monotonic probability, so for single variable case, single random variable, we have that fx of x is non-decreasing, right? So it either increases or it remains flat, right? Now you can talk about being non-decreasing in this way, that for every a less than or equal to b, it must be the case that fx of a, then fx of a is less than or equal to fx of b, right? This is another way of saying that the function is non-decreasing. If you choose a less than or equal to b, it must be the case that the CDF evaluated at a is less than or equal to the CDF evaluated at b, or you can say, rewrite this thing as the CDF of b minus the CDF of a greater than or equal to 0. How can we do something similar like in multiple dimensions if you have a random vector, right? So things become like a bit more complicated. So we have something called the rectangle inequality, and I will say it first and then let's think about it. So you basically choose n numbers, an, and another n numbers, and each, so basically this vector is less than this vector element-wise, which means that a1 is less than or equal to b1, a2 is less than or equal to b2, all the way to an being less than or equal to bn. Okay, so we have ak is less than or we can make it, let's follow the writing here, strict less than, won't matter, for every k. Now there is a quantity that should give you something positive. This is the quantity. So it is a summation. How many sums do we have? We have big N sums. Each summation index just take one of two values. Then we have -1 to the power the sum of the indices. Then we have the CDF, and it is evaluated at x1 I1, x2 I2 till xn in, where xk, if I put the index here, if the index is equal to 1, then I am talking about AK, and if I put the index equal to, I am talking about BK. And what are the A's and B's? Again, those are numbers, n numbers, A1 till AN, another n numbers, B1 to Bn, and it's always the case that each number in this vector is less than the respective number in the other vector. Of course, if you look at something like this, it's not clear at all what is this thing. So I think like the best way to understand it is like to do it in the special case when big N is equal to 2. Okay, so when big N is equal to 2, we can actually like see exactly what is going on and why this quantity must be greater than or equal to 0. Okay, so what is this quantity when N is equal to 2? So we have two summation indices. I1 equals 1 to 2. I2 is equal 1 to 2, right? And then we have -1 to the power of the sum of the two indices, I1 and I2. And then we have the CDF. Now we have just two random variables because we are focusing on the case when the dimension is 2. We have just two guys. And then we have x1, I1, x2, I2. How many terms do we have? So we have 2 terms in the first sum, 2 terms in the second sum. So in total we have 4 terms. Okay, first go. If both indices are equal to 1, so we'll have -1 to the power 1 plus 1. And then we have f of x1, comma x2, and then x1, 1. Again, if this is 1, we are talking about a1. x2, 1 also, because again, both indices now are equal to 1. So if we have a 1, then this is basically, so if xk, comma 1, so if we have x2, comma I2, and I2 is equal to 1, it becomes A2. Like this. Okay, so what is the next term? Let's make I1. Okay, so let's make I1 equals 2. So this is I1, and I2 equals 1. X1, X2. So what do we have? So we will have X1, comma 2. What is X1, comma 2? What is X1, comma 2? It is B1, right? A direct application of this thing. X1, comma 2 is B1. And then we have X2, comma I2. I2 is equal to 1. So this will be X2, comma 1. Any xk, comma 1 is basically ak. So x2, comma 1 will be equal to b, will be equal to a2. A2, a direct application of this thing. Okay, so b1, comma, sorry, a2. Then we have, let's make this guy 1 and the other guy 2. So this will be I1 and this will be I2. Fx1, x2. What do we have here? Again, the first guy is x1, comma I1. In our case, it is I1 is equal to 1. So it is x1, comma 1. If this second guy is 1, it can be 1 or 2. If it's 1, then we are talking about the A's, A1. Okay, so this will be A1. But what about the second guy, x2, comma I2? What is I2 in our case? It is 2. So this is x2, comma 2. If the second index is 2, then we are talking about the B's. What B we are talking about? Depending on the first index. So it will be B2. So this will be B2, right? And then the last term is plus I to the power 2 plus 2. So both guys are basically equal to 2. And you can verify that in this case, you will get B1, comma B2. And basically, minus 1 to the power an even number is 1. Minus 1 to the power an odd number is minus 1. And so basically you get something like this. So it's better than the summation. Okay, it's better than the summation, but it is still not clear what those guys are. So it is like the joint CDF evaluated at A1, A2, A1, B2 with a minus sign, A1, B1, A2 with a minus sign, and then B1, B2 with a plus sign. What is this thing? So in the next lecture, we will show that actually this is a probability. And it is not a difficult probability. It is the probability of this event here. That x1 is living between a1 and b1, and that x2 is living between a2 and b2, right? So if this thing is a probability, right, it should be non-negative, right? Otherwise, we'll have a negative probability.